Hey everybody, I'm Danny. I'm a software engineer at Formlabs, and I work on our desktop slicer called Preform. And what's interesting about Preform is it's one slicer that supports a wide variety of printers, obviously. Our product line over the years has gotten pretty large. And what you'll discover is that the technology that we deploy between each of these printers varies pretty widely, and so there's no one-size-fits-all config. And so I built the print settings editor in Preform in 2023, and the hardest challenge by far with shipping that feature was stabilizing our schema. And that experience was challenging in a bunch of ways, but chief of which was just understanding the way the existing thing worked, right? So first of all, here's a couple of screenshots of the print settings editor. At first, it just looks like a form, right, where you're just filling out all of the config that you want to upload to the printer. But it's a little bit more complicated in that what we're exposing here is each of our material files. So between the various printers, we offer a portfolio of materials. They have a bunch of different configuration associated with them. And so getting that thing to a place where it doesn't require massive manual updating between each version of Preform as the schema changes was the real challenge here. I've attached this picture of a paper towel dispenser from the bathroom in our HQ. And this resonated with me because usually you sort of wave your hand underneath this thing and it dispenses a paper towel. But inevitably, there's always somebody who comes by and tears the cover off of this thing to get at the button underneath it. And that button holds a special place in my heart. And that's sort of what I look at the PSE as. For the vast majority of our users, using the Formlabs provided print settings works great. But for the occasional user, they just want to tear the cover off and get at the config underneath. So I already kind of mentioned this, but there's a lot of variability in the config between our printers. It changes a ton, and what I'm hoping to discuss today is two sort of components that give Formlabs a competitive edge. On one hand, we try every couple of years to ship a printer that has new technology in the market, right? We're trying to build something that didn't exist before, and that requires a ton of iteration on our configuration. But the second piece of that puzzle is trying to get the highest print success rate that we possibly can and to support as many materials as we can. And so while that's the case, we're trying to keep our config as stable as possible. So this is what I was just describing. By far, what I want to stress with this talk, we're going to jump into a couple of examples of different projects that I worked on to make this whole system work. But I'm not trying to wow you with the complexity of those examples. I think they fit well into a talk like this, but the goal isn't really to show you how clever I am. The goal is to show you that sitting down with the consumers of your product is the best way to figure out what you actually need to build. And at Formlabs, the main consumers of our product were actually our internal teams. We have a material development team. These are the guys that are trying to find brand new materials to print using our printers. We have R&D, obviously, which I was describing, and those guys are trying to figure out brand new technology. And we have a SetOps team. And I really love spending time with the SetOps team. They are the people who benefited the most, I would say, from the changes that I worked on. And they just don't want you to touch the schema at all. They want it to be as stable as possible. Whatever you do, please don't invalidate my files because it kills my research and it costs us all money, right? So starting this talk, we're going to divide the talk in two. I'm going to talk about how we can iterate on our schema as quickly as possible for the first half. And for the second half, how we can slow it way down, lock it in place, and hopefully, by changes to our process, enforce the idea that the schema shouldn't change, or should change in a sort of regulated environment. Cool. So reducing friction, in our case, our desktop slicer is written in C++. C++ is a language that doesn't have reflection. And for that reason, we need to kind of shoehorn in a solution that gets us where we need to be when it comes to reducing friction when changing our schema file. So the goal here is that all I'm changing is the schema itself, and all of the sort of pieces that cascade down as a result of the schema are updating automatically. And there's two main components to that, right? There's the generated UI, which this is the editor that I was showing earlier. But there's also this C++ header file. And I'll explain in a second what's so attractive about the C++ header. The main goal of this is, like I mentioned earlier, our slicer is the main consumer of our config, right? Like, We are passing in a JSON file and reading it. We're using that to instantiate a C++ class. And our slicer is the one who's saying, okay, what's my exposure? What's the value of the heater, right? The temperature. And it's generating code that we ultimately upload to our printers. And so in that sense, the slicer is the thing that we really want to feed our config into. And as I mentioned earlier, it's written in C++, right? So ideally, I'm consuming a header file. I'm using that header file in a way that if I misuse it, I know about it as soon as possible, right? If I'm using some kind of generic type because it's easier and it doesn't cause friction when I change my config, I'm also introducing this possibility of error when it comes to consuming the thing. So here's the high-level plan. At configuration time, we're going to invoke a Python script. That Python script is going to generate the C++ code that we need to consume in our slicer. And then at build time, we're actually going to consume it, and we're going to pull in all of our config and slice. So not much to say, honestly, about the generated file. This thing is pretty simple. And that's kind of the goal. Like, ultimately, the needs of this thing are determined by the serialization itself. I have one file that I need to serialize. It has a whole bunch of values in it. And if I need to write abstractions over top of that, I can do so, right? Like, I can take little bits and pieces of this and use those to feed specific settings and do specific things. But that's not really the goal right here. We're just trying to build a huge, long list of config. And there is some complexity in this system that I'm sort of hand-waving away, but I'm hand-waving it away. So we have getters, we have setters with validation. I showed in the previous slide that we have a constructor and equality and things like that. And then we can do anything else that requires just enumerating all of our members one at a time. So we have our to.json and from JSON. We have this kind of fancy all of named fields thing, which acts find-like in that I can look for the field by a given name and exit when I've found it. So jumping into the implementation, here's the goal. At the CMake call site, I'm going to format all of my paths. I'm going to figure out what the names are of the specific C++ files that I need to generate. I'm going to invoke my Python script, and I'm going to create a library, but we'll get to that later. Here's the Python main. I'll give you a second to read it, but there's 3 main steps. I'm parsing the schema into memory by loading the JSON file. I'm generating a bunch of C++ code, and then I'm writing that to some output files that I can pass along to CMake at the end. Cool. Here's the implementation. I have this virtual parameter class. The idea here is that each of the config options ultimately conform to this one interface. And I can do all the type-specific stuff in a specialized instance of each of these things. So I'll show those here. So here's my string param and my int param. In the case of string, I have a regex, and in the case of int, I have a min and max. I won't spend too much time discussing this because I think it's pretty self-explanatory. I'm deriving from that param class that I showed earlier, and the idea here is I'm just like adding whatever additional options I want to support in my schema. Finally, I have my parse schema function. I'm visiting the big schema file, building up all of my various params, and I'm going to use that to generate my C++. Finally, here's the generating of the C++. I have an f string in Python. I'm just like showing the exact format that I want. I've skipped a few steps here, but you get the idea. Cool. So what we really like about this system is that there's almost 0 friction when changing the schema. All I have to do is modify it. And if I rebuild, obviously my configuration, I can point it to reconfigure when that file is changed. I get a new config library, and anything that depends on that config library rebuilds as well. So what's really nice about this is I change the config once, and then any parts of the slicer that depended on the previous config and are now misusing the new one, they break, and the compiler tells me that. The cons of this is that changes to the implementation affect every single piece of configuration. So if I have any kind of special casing where I want to do configuration over here in a slightly different way, it becomes harder to do that. And the reason I bring this up is the same point I was trying to make earlier, that the Form 4 uses the same exact configuration system as the Form 3 and the Form 2 and all of our other product line, even though the content of the schema is different. So if I decide, for our new product that I want to actually use a different configuration system, well, it's pretty hard because I have to change everything, or maybe create a new version of this library I just showed you. And then finally, new hires are not used to this like generated source thing. So people try to go in and modify this library that's generated, and then they build, and all of their modifications are lost, and they're like, what is this thing? But that's not too hard to explain. Maybe I'll just send them the YouTube video. Cool. So next thing I really want to stress in this is that this talk is not so much about like I mentioned earlier how fancy this is, but rather trying to understand when we need to do what, right? When we're developing the printers, when we're changing the config all the time, we want to reduce friction. But when it's time to freeze things and lock things in place and actually have something stable, we need to have a different approach. And so part 2 of this talk is the different approach. Basically, as soon as we ship the product, especially now that we have the print settings editor, people start making their own material files, and they really want them to be consistent. They really, really don't want us to change the meaning of the config, especially like the actual use of it in the slicer. But more importantly, like they don't want to import their old material files in preform and see that it's broken or that it doesn't import. So we have a different approach for how we can handle that. And I want to stress that this isn't about adding arbitrary friction. I mentioned that it was a benefit that we had low friction when it was changing the schema earlier, but we're not just adding it for the sake of adding it, right? That's what code review is for. That's what like our own team is supposed to be enforcing. Okay, so the goal here, attach a version number to the schema, alert when the schema breaks, formalize schema changes, so we say which changes are you allowed to make to the schema at this time, and then build some kind of automatic system that migrates the old file after you import it into preform, or as you import it into preform. So, for the implementation of that system, I put together this little diagram. What we discovered is we could do this in sort of 3 distinct steps. In step 1, we modify the schema. We install a couple of unit tests, and these are run as part of our CI pipeline. And a unit test fails and says, you can't merge this. You need to do more stuff. So this unit test fails and says, we detected changes. You need to address them. Step 2, we provide a tool that a developer can just run, and it's going to maybe add a migration stub or maybe commit the change set that I mentioned. It's going to do something. And just by running that tool, we pass the previous test and we fail a new one. And the new one is saying, you need to describe what you just did, right? So in one step, we caught the changes to the change set. In the next step, we caught the changes to the schema. In the next step, you need to do something. You need to act on those changes. And then finally, in step 3, this is where the developer can actually say, here's what I changed. Here's what I meant to do. And ideally, by the end of this, when a material file is imported into preform, we're doing something to it. And that's step 3 here. So in terms of the implementation of this system, it's these 5 things. I'll give everybody a chance to read it, but basic idea. Keep a shadow schema in our source code. Use the shadow schema and the latest schema to find differences. Write a tool that takes those differences, puts them somewhere, ideally in the source code, and then build in some kind of system that encourages our developers to take that result, put it over here, write a migration, pass all the unit tests, and move on with their lives. Cool. Step 1. Make a copy of the schema that we're calling this shadow schema thing. That's pretty simple. This is just a copy of our schema file. Step 2, and this has a nice relationship with the stuff that we talked about over in the first half of this presentation. We can use that in-memory Python representation that I showed to actually parse out the differences in the schema that we care about. If I was just doing like a JSON diff, of course I could write my own tool to filter the parts of that or the differences there that I actually care about. And as an example, I mean like if I just change the description of a parameter, I don't really need to like make any changes. I don't need to inconvenience a developer when unit tests fail just for that. So we reuse our Python representation here to say, actually we only care when you change the default value maybe, or the minimum, or the maximum, and so on. So we build our diff tool. Step 3, a unit test fails, right? So we wrote all these changes to a file, we consume the file in our C++ unit test, and it just looks that it's not empty. Step 4, this is our tool. This thing is going to take the change set generated in step 2, it's going to write it into our source code, and it's going to bump the shadow schema. So this way, if I were to rerun the whole system, there's no changes anymore. But there's a little artifact that was left behind, and that's what I'm going to act on in the next slide. And finally, step 5, we give developers an API that they can use to describe what they were trying to change, what the goal of their changes to the schema actually were. So this is my favorite part of this system, by the way. I like that, first of all, the developer isn't just taking some abstract instance of the parameters and modifying it in some arbitrary way. They're calling specific functions and saying, here's the thing that I was trying to do. And I mentioned a little bit earlier about how sitting down with people and actually talking about the way your product is consumed is so important. This is kind of the same theme, right? Like, I sat down with the print pipeline engineers at Formlabs and I said, how do you guys change the schema? And they gave me a big list, or they told me a bunch of stuff and I turned that into a big list. This is a subset of it, but you get the idea. Maybe we change the units of something and the value needs to be multiplied by some scalar. It's that kind of thing. Okay. So that brings us to the pros and cons of this system. First of all, it's great that we can offer publicly a material file now. I can give a bunch of people the version of the file from the previous version of Preform, and when they import that same file into the next version, it just works, right? I can't stress enough how much of a nightmare this was for like 10 years for Formlabs. We had material files. There was a huge effort every single release to look at all the differences in the schema, bring all of these files up to date, and then hope and pray that everything worked the same way. Now that it's formalized, we have a little bit more of an expectation of how everything should work. And of course, there are some cons here. The whole point of part 1 was that I didn't want to inhibit our developers. I didn't want to add friction, right? Well, now there's a whole bunch of friction. So we have to do this at the right time. And that brings me to my final slide. What we learned, again, after sitting down with our settings optimization team, with our material developers, with our preform developers, was that they weren't doing all of this stuff at the same time, that development had a life cycle, right? And that in the early stages of a printer's development, the schema was changing a ton, and by the end, the schema was changing very little. And that was inversely correlated with the consumption of the schema. So early on, nobody has material files, but the schema itself is changing all the time. After the product is shipped, we lock the schema in place. The schema hopefully doesn't change very much, and schema consumption or material file use goes way, way up. Okay, 2 examples. I hope I conveyed some meaning about the way we use schema files at Formlabs, and I'm happy to answer any questions if anybody has any.